There are three folders available to us. The small data folder contains the small training data set. The test data folder contains the large training data set, and the results folder contains the output from a previously conducted study over a large data set. Before we run ArcGIS Pro, it is imperative for us to install deep learning libraries, because without this we will not be able to perform the workflow on the ArcGIS Pro. There are three pillars in a deep learning workflow, which is first to prepare the training data. The second one is to train the model using the training data. And third is to use the model to identify the objective from the unseen data. Once we set up ArcGIS Pro and reference it to the folder where all these data sets are stored, we can initiate the first step, which is to train the deep learning classification model using the small training data set. Why do we feel the need to accurately classify power lines? For a very simple reason is because it is a sensitive infrastructure which is exposed to risk such as fire from adjacent trees, obstructions on its way, hawkers on the ground, and so on and so forth. There are 4 million data points in our small training LiDAR dataset, and these have already been classified as building, ground, and several other types. The most important being serial number 14, which is the conductor wires, which is essentially the power lines. So, in the 4 million data points, there are roughly 21,000 points which have been classified as power lines. We will load this LiDAR dataset, which is the small training dataset, onto the map view. We can begin exploring the three-dimensional colorful LiDAR dataset, which is on the map view now. The elevation values range from 811 feet to 1238 feet, which signifies that this is a slightly hilly terrain. You can see the outline of the power line in the map view. It is kind of, you can say, easy to discern. And you can also see that it is surrounded by a dense vegetation, a whole lot of what seems to be like coniferous trees. We will also load the validation dataset onto the view. The validation dataset lies adjacent to the small training dataset. The presence of this particular dataset helps the deep learning model to work effectively in a wide variety of situations. To explain this using the sunflower example once again, we not only want to be able to detect sunflowers in similar settings, let's say in a small garden, but then we also want the model to be able to detect sunflowers in a large forest also. So the validation dataset typically is much more diverse in nature and different to the training sample dataset. Instead of displaying the LiDAR point cloud as per the elevation, we've now changed the symbology to display it as per the classification. So the power lines are currently visualized in yellow color, transmission towers in blue color, the trees and vegetation in green, and so on and so forth. Similarly, we'll apply the same symbology to the validation layer as well. Symbolizing as per the classification helps us to easily spot the various features on the map view. Next up, we'll begin the training process. In the geoprocessing tool, we will refer to the prepare point cloud using the training data. There are several technical parameters involved, and the purpose of this exercise is not to explain them. However, at a broad level, we are redirecting the geoprocessing tool to use the training small dataset as the input point cloud. There is a training boundary, as in, you know that the particular power line runs through the middle of the dataset. So you have setting a boundary that, please do not process the points which are far away from that center point. Again, the same rule applies for the validation point cloud and its boundary. The block size is a technical parameter. It is essentially we are telling the software is that 82 feet is the potential size of a power line between two transmission towers, and you basically use that particular block size to classify the DL algorithm. The histogram output helps us to examine whether the number of LiDAR points within each block is sufficient or not. If it isn't, then we run the risk called subsampling, which kind of distorts the classification algorithm's effectiveness. Because there are sufficient LiDAR points within each block, that essentially tells us that we can accurately detect the power lines from the particular block. Thereafter, we will use the next tool, which is the train point cloud classification method. In this, we use the output of the previous step, which is the training data. This becomes the part of the input training data. Also, we set minimum points per block as 2000, because we know that if there is any block which has less than 2000 points, it is surely not going to contain very many power line features, as potentially it is located far away from the center point of the data set where there is a conglomeration of the power line LiDAR points. What you also need to know is that it is not always that we strive perfection from the classification model. Sometimes we are limited by the computing resources we have. Sometimes we are limited by the time we have at our disposal. So we have to strike a balance where we need to get a certain level of accuracy also from the data set, as well as to minimize the resource and time consumption also. So for example, in this particular workflow, the recommended GPU size is very high. But then if somebody has a lower GPU, then he has to relax the parameters so as to make the processing quicker and get a seemingly effective result as well. One point I would like to clarify is that these tools take a lot of time, and while the video is fast forwarded to account for ease of viewing, these steps are not very quick to operate. While this training takes a long time to complete, we can monitor the progress. So you can see that there are certain layers of information which are continuously being added at regular intervals. There is something known as an epoch, which is a kind of a cycle in which the entire training data set is passing through the neural network of the deep learning algorithm. We are basically processing this classification model across 10 epochs. Then there is something known as a training loss and a validation loss. The training loss indicates how well the deep learning model is working on the small training data set, whereas the validation loss indicates how well the model is working with the validation data set. Both these loss figures tend to decrease with each passing epoch, at least during the initial phases, which signifies to us that the model is learning as and when more and more data passes through it and the more iteration it does. To explain precision and recall values in terms of the sunflower example, precision is if the model detects there are 10 sunflowers and out of which there are actually 8 sunflowers, that means that the precision is 80%. Whereas if the model is able to detect 6 sunflowers in an image and there are actually 10 sunflowers in the particular image, then the recall value is 60%. For this particular analysis, the recall value is very important to us because we want to know the number of true positives in comparison to the actual objects. The processing step is complete. In the final epoch, the recall value is 86%, which is alright considering we had trained it using a small sampling of points only. As part of the completion step, a few graphs and Excel sheets have been generated. For example, this graph shows how well the model was responding to the training dataset as well as the validation dataset. We see that there was a symmetry in between the model's response to both these type of datasets. When we visualize the performance of this particular model epoch wise, we can see that there are two categories, two levels of classification, right? We had classified the LiDAR dataset based on the whether it is a power line or not. So when we sort this dataset, we will see in which epoch did the classification model perform the best. It is in epoch number 4, where the model had the highest recall value, as in it performed the maximum number of accurate detections of power lines. Make note that this is the performance in the small data set. The large data set has been trained on a 24 GPU system, which allowed the person who had run that analysis to set more rigid parameters and identify the best recall value from that particular system. When we see the output Excel of that particular workflow and examine in which epoch was the recall value the highest, there were a sum total of 22 epochs compared to the 10 epochs which we had run on our system. So out of these 22 epochs, in which epoch was the wire conductor having the best recall value is for us the objective in this particular processing step. We can find that in epoch number 16, the recall value was 92%, which means that out of every 100 power lines which are there, power line points which are there, this particular model was able to detect 92 points accurately, which is a much better performance rate compared to the 85% which we had done using the small data set. Hence, therefore, we will train the classification model using this particular epoch and then ask the model to identify the power lines in a new data set which comprises 2 million plus laser data points and to identify the power lines from it. This particular test data set is currently visible on your screen in the 3D mode. We will classify the layer as per its classification. Because it's unseen data, there is no classification. So each and every point is unassigned. So this is our objective, which is to use the pre-trained model at the best epoch to identify which points in this particular LiDAR dataset are power lines. So we will run the classify point cloud using train model tool, in which we will link the parameters to the various datasets. We already have the target point cloud test dataset, which we extracted from the zip file at the beginning of this video. Also, there is a model definition, which we will basically link to epoch number 16, where we found the best performance. Subsequently, we will ask the model to specifically classify the power lines, because that is what our objective is. So the remaining classifications are not important to us. We want to know the power line classification. Once we've run this tool, we need to symbolize it so as to display the classification which has been generated as the output of this model. You can see the bright yellow in between the brown points. So that bright yellow is the power lines. The transmission towers have not been classified. So what we are just seeing is the power lines in the dense forest landscape. Isn't this wonderful? How the DL model has worked on unseen data using a pre-trained model and identify what are the power lines. Now, these yellow lines are actually not lines, these are small points. We can actually link up these points to create a line using the extract power lines tool, which is specifically built for such applications. The parameters are simple. We will use the LiDAR dataset as well as the output generated and request the tool to create a line out of the point cloud dataset. The dataset has been created, but it is not clearly visible at the moment because the point cloud layer is also active. You may be able to see a patch of red in between the yellow. That is exactly the power line which has been generated using this tool. If we switch off the older layer, you can see the power lines have been identified with a great deal of accuracy. So we get to know the geometry, we get to know the elevation and a variety of spatial information from using this step. With this, we come to the conclusion of our Caselet number 3, which is to extract power lines from LiDAR dataset. Thanks for watching.